All right, so this is our last one. We've talked about how to write these formulas and how to get names of ionic compounds, and each of them had different things in them. We had type 1 metals, which are the known charge ones. We always know the charge of those metals. We had type 2 metals, and we always know the charge, or we do not always know the charge to type 2 metals. We have to figure out what the charge is based off of the other thing that it's bonded to in the ionic bond. And now we have polyatomic ions. Polyatomic ions, we obviously always know the charge on. However, there's some differences that we have to deal with when it comes to actually naming them. So each one of these things has different naming convention, and we have to deal with them in different ways, and we have to think about them slightly differently. But ultimately, they're all ionic compounds. They all have to meet those criteria for being ionic and for being a compound, which are they are a metal, a positively charged thing and a negatively charged thing that are attracted through that positive negative charge. That's what causes, or that's why we call it an ionic. And they are a compound because everything in there has a full outer octet. So all of our elements or all of our ions in there have a full outer octet. And they also will be neutral when we put them together. So the last thing that we cover here is the polyatomic ions. Let's go ahead and just get into that. We'll start off by giving some background information about the polyatomic ions pretty quick, and then we'll go through a couple, maybe just one or two of these examples that are in this packet. So give me 1 second to pull this up. So as you may know, since you just took a quiz on it, polyatomic ions are covalently bonded atoms, and they act as a single ion. So it could be multiple or many, which is what poly means, many atoms, polyatomic, and they are an ion. They have a charge to them. There's only one that we really encounter in this class. There's actually a second one that we could potentially encounter, the hydronium or H3O+. But there's only one positive ion that's super important for us, and that is the NH4 plus ammonium. The rest of them are negatively charged, and I've been asked a couple times in class, why are they this charge or the other? If you were to draw the full Lewis structure of these things and kind of think about what they could do, you notice that they'd have like 1 or 2 or 3 holes where they could fit an electron in, and so they are pretty electronegative themselves, and they will pull those electrons off of a metal and become negatively charged by 1 or 2 or 3 because they have spaces to fit those electrons in. So these are our polyatomic ions that you've seen and kind of learned. I think I added one here. I'll highlight that in like an orangish color, that HCO3 1 minus. Notice how carbonate is on your list. It is CO3 2 minus. But if I toss a positively charged hydrogen on that, I make this thing called bicarbonate, which is that stuff that's in baking soda, except there's also a sodium with it. So sodium bicarbonate is baking soda, and that is a ionic compound. It's a crystalline solid, forms a powder if you crush it up real good and put it into a box with some kind of hammer and arm on it. But it is definitely an ionic compound. Okay, so we know the conditions for an ionic compound. We know about type 1 metals, we know about type 2 metals, and now let's get into some polyatomic stuff and see what we can do. So here is my first page. There's no polyatomic ions here. We're going to skip over to the next page. I see one polyatomic. Let's go ahead and skip it again. Here we go. There's a couple here. Let's look at, first of all, I'll probably do maybe 3 examples real quick. What happened there? Weird. Okay. I saw an ammonium here, I thought. No, maybe not. Okay, so let's look at ammonium and fluorine. When these two things come together, we already know the charge on both of these, right? So the symbol for ammonium, the polyatomic ion, is NH4, and it has a charge of +1. Fluorine is F, and it will have a 1 minus charge, or 1 minus oxidization number. If I do my crisscross thing, I'll have a 1 going with the fluorine, I'll have a 1 going with the NH4, and so what I'll write then is NH4F. The type of naming rule that I will use is it is ionic, it is a polyatomic, and a non-metal. So when we're doing these rules and you're filling in this rule section, you need to write the type of compound, the type of positive thing, and then the type of negative thing. So it could be ionic metal type 1 and the non-metal. It could be ionic metal 1 and polyatomic. It could be ionic and type 2 metal and non-metal. It could be ionic type 2 and polyatomic. It could be ionic and polyatomic and non-metal. It could be ionic and metal and polyatomic. So there's a lot of different variables, ways that we can arrange these things. But ultimately, they all follow some of the same rules or most of the same rules with just a few slight differences that we need to be aware of. Okay, so NH4F is our ammonium fluoride, right? And just like before, we were going to not change the first one, and we will call it just our ammonium. I think there's two N's in it, or M's in it. Yep, there is. Okay, ammonium fluoride. There we go. We're done. We could draw an ammonium, but when we draw a polyatomic, anytime that we draw a polyatomic, we always have a little bracket, square bracket around it. So I'll have an NH4. It's already a plus charge because it's an ion already. It goes into the reaction as an ion. And then it will react with this fluorine, which will represent as an F with 6 dots on it, and fluorine is negative. So there we go. That is a Lewis structure for everything. And we could also start, like picking apart that nitrogen and that hydrogen and those 4 hydrogens and also that fluorine. And really interestingly enough, what's happening here is, if you remember what we talked about when we talked about hydrogen bonding in intermolecular forces, this is like an ammonia, and ammonia is just NH3, right? But ammonia has a nitrogen on it with a lone pair. And so a hydrogen can get next to that nitrogen and what we call it, hydrogen bond. I also said that fluorines can participate in hydrogen bonds. And so what will happen is there's kind of a hydrogen bond situation between this ammonia and this fluorine. However, the ammonium really keeps the hydrogen to itself more than it goes to the fluorine, and so is mostly a part of the NH3 and not really a part of the fluorine thing. Together, though, we could draw an entire Lewis structure that would look something like this. We'd have a nitrogen, I'd have a lone pair of electrons on my nitrogen, and 3 hydrogens. This is my ammonia model or molecule. If I go and I remove too much. Okay, so if I remove that lone pair and I replace it with a bond, and on the other end of that bond I put a hydrogen, that's like a hydrogen bond, right? It's really, really close to being a hydrogen bond. But this whole structure here is now a +1 charge, and then our negatively charged fluorine will have done that because when this ammonium forms, it's a single neutral hydrogen with an electron, and it forms a bond with a nitrogen, right? So we have a hydrogen with an electron bonding to a nitrogen now. So that's 3 electrons because the hydrogen came into this with 1 electron, the nitrogen came in this bond with a lone pair of electrons, and so overall that is 3 electrons. Those 3 electrons, 2 of them will participate in this bond to make a ammonium ion, and the other electron will get absorbed by the fluorine. So that gives fluorine its negative characteristic, -1 charge. There we go. That is our structure and all the charges and the name and the type of naming rule and all that stuff we've done right there. We're good. Let's look at one more. Let's say I have lithium hydroxide, which is Li. Remember, lithium is going to have 1 electron. It's going to lose that 1 electron and become a +1 charge. A hydroxide is a polyatomic ion with an OH, and it has a -1 charge. Oh, I don't want to do it. If I look at the total number of charges and I do my crisscrossing thing, I put my 1 with my lithium. Lithium has a 1 on it. It goes to the hydroxide, and I will call that LiOH. To name, or the naming convention we should use is, again, this is an ionic bond. It will have a type 1 metal. Lithium is that first column, which is one of the type 1 metals. And the other thing it will have is a polyatomic. No, it's probably kind of hard to read. Let me zoom in just a tad on that. So again, this forms an ionic bond, so this whole thing is ionic. There is a type 1 metal. And the other thing in there is a polyatomic ion. If I want to name this thing, the naming convention is very similar to what you've seen before with ionic ones. There's no prefixes. It's just going to be the ammonium. Or sorry, not ammonium. I'm looking at the other one we just did. Is going to be lithium. And then hydroxide. There's only one of each. I don't do prefixes, so it's not lithium monohydroxide. It's just lithium hydroxide. And I can do a similar thing here for my Lewis structure. I will have an O bonded to a hydrogen, and that's it. That's my OH model. And then from there, I will have a lithium coming along. And the whole thing has a minus charge. I'll have a lithium come along. And what you might notice is here I have 1, 2, 3, 4, 5, 6 electrons. So a lithium needs to, I have 8 electrons around the hydrogen. The lithium is a positive charge thing, so it's just an Li plus. I could flip these around. I could call it also, that's a before and after arrow. I could call it, we'll do this squiggly arrow to say that this is just another way that we could do things. Could call it, or sorry, I could draw it as lithium plus with a OH next to it. Either way, you can see that this is a 1 hydroxide to 1 lithium type of situation, and so these are both have subscripts of 1, but we don't write subscripts of 1s. Just having it there in the chemical formula name means it is in the compound. There we go. We're good with our lithium hydroxide. Let's do one more, this little advanced one here, and it is ammonium nitrate. So I have NH4 with a positive charge, and then I have nitrate, which I think is NO3 minus. I always double check that if we wanted to. Maybe we can't. I could look it up. Give me a second. So as it turns out, yes, indeed, NO3 minus is the nitrate. NO2 minus 1 is our nitrite. My chemical formula for this will be NH4 plus NO3. So I don't need a plus. When you do your actual formulas, you should not have pluses and minuses on them. Make sure you never do that. You will lose points for them. Pluses and minuses are useful for doing the crisscrossing thing, but once you've done that crisscrossing thing, you don't need those plus and minuses anymore because the whole thing should be neutral. All right, so this is NH4NO3. The naming rule I'd have to follow here is that it is ionic, pretty clearly. We're always going to have ionic compounds for this unit. Sorry, not this unit, but this worksheet. We will have an ionic. It will have a polyatomic ion bonded to a polyatomic ion. There we go. That's our naming rule that we should use. Chemical name for this would be ammonium nitrate. It's still nitrate. There's no fancy words for it. It's just what it is. It is nitrate. And there's not much else to it. So ammonium and nitrate, if I could, draw a Lewis structure, but I think at this point you should be okay with it. I just want to point one thing out about these polyatomic ions and how they are named and how their formulas are written. So if I have something like, let's say magnesium, which has a plus or a 2 plus charge, and let's say I had something like phosphate, which has a 3 minus charge. If I do this crisscrossing, what I should see is then Mg3, I'll have 3 Mgs, but also I will have 2 of these PO4s. So now, how do I write this? Because you just saw me write that 2. Maybe I put it down here, right? But that doesn't look like PO4 2. There's 2 PO4s. It looks like that's a phosphorus and then 42 oxygens. That's pretty unclear what's going on here. To clarify where things go and what these numbers mean, we really need to be careful because, again, a 42 is very different from a 4 when we're talking about the number of oxygens in an item. That would be a hyper phosphate. Yes. Okay, so MgPO4. To deal with that and this confusion around where this number goes, we always enclose a polyatomic ion with parentheses, and then we put the number of polyatomic ions outside. So when we do our crisscrossing, that 2 came from our magnesium, this 3 came from our phosphate. And again, the phosphate is now sitting inside of parentheses. So be careful about your parentheses, though. The only time you need them is when there is more than one polyatomic ion out there. So Mg3, parentheses, PO42, right? Mg3, inside of the parentheses, PO4, close parentheses, and then subscript 2 to show that there are 2 of those PO4s for every 3 Mgs or something like that. So this is our polyatomic ions. Again, we could do this in a couple of different ways, but ultimately you just need to know these naming conventions. You need to know these rules for writing out the chemical formulas, and you'll probably be fine. So that is all I gotta say to you guys. I hope you guys have a good one. If I don't see you on Friday, enjoy your weekend and your Thanksgiving break, and we'll see you back on that Monday, fresh-faced, refreshed, and ready to go and really tackle the rest of this ionic stuff and then prepare for our semester summit. So have a good one. Enjoy.